Welcome to this lecture. We will continue our discussion on the aqueous carbonic inclusions and their implications to thermobarometry. We have discussed to some degree of details the procedure, one of the procedures which you could adopt for calculation of minimum pressure of entrapment from the total the temperature of total homogenization with the compositional parameter of the aqueous component and the density of the carbonic liquid known, and we as we saw that this calculation procedure is pretty elaborate, and there has been many improvement many attempts to improve such formulations to get the accurate value of density and the dP by dt slope, which actually is very important in understanding processes in which such kind of aqueous carbonic fluid, and we see that such kind of mixed aqueous carbonic fluid is actually more dominant in deeper arc processes, whether it is metamorphism or mineralization. And the interesting thing about this particular system and why is it very important is that there is a bit of a difference. The fluid undergoes a drastic difference in its chemistry when it splits from a homogeneous one phase condition to a heterogeneous two liquid condition, and many processes like important because it also controls the solubility of many of the metals in such kind of mixed fluid. So, it has got tremendous implications to understanding ore forming processes where the processes take place at temperature pressure conditions which are within these ranges that we are considering. So, continuing our exercise on thermobarometric exercise on thermobarometric implications for mixed aqueous carbonic inclusions. So, we just to recapitulate, we can use the same logic that we have used for pure aqueous biphase inclusions or for any other inclusion where the entrapment is homogeneous and the heterogeneity that develops inside the inclusion cavity is a result of post entrapment phase change, and we can determine the temperature pressure conditions as we did for a aqueous biphase inclusion by knowing the vapor pressure. In this case, we are also able to calculate the pressure and the density of the inclusion by an elaborate method which we discussed before. And then as it happens, suppose the fluid is anywhere between anything to consider the rho 1 or rho 2 or rho 3 or rho 4, where these are the rho Th, that is rho total, you can say that density at total homogenization. So, they could have followed any of these isocores the way it is shown, and the temperature pressure condition of entrapment could be anywhere on the isocore, and then it is that if we have an independent consideration of either temperature or pressure, that means if you are working on an assemblage which is a good thermometer, then both temperature and pressure could be found out from the once we know the isocore. So, constructing the isocore, the accurate isocore in this H2O CO2 NaCl system is very crucial, and we know that even though we are drawing them as roughly as straight lines, but from the if we construct them the isocores from the modified Redlich-Kwong equation, then there is a little bit of a non-linearity that will be there, and there rather would be more friendly curves rather than just straight lines in this mixed H2O CO2 system. And so, this is one of the ways that temperature pressure could be obtained, and any independent estimate of temperature or pressure. Now, let us consider the situation in which we may not need any pressure correction, or we the pressure temperature values need not have to come from any independent, or we do not have to look for any other independent source of temperature or pressure. This situation is somewhat analogous to the situation which we discussed for boiling conditions in a aqueous fluid. So, what is boiling in an aqueous fluid? The separation of a vapor phase can be thought of as an analogous situation here is that unmixing of a homogeneous aqueous carbonic fluid to a heterogeneous combination of the two liquid, or one of them carbon dioxide could be vapor depending on the pressure temperature condition that where we are. These are essentially TX02 diagram. So, here we will consider a situation where the thermobarometry or the total homogenization temperature and the pressure calculated from that will actually be the true temperature or pressure of trapping. If we consider that the entrapment was actually taking place on the solvers. Say for example, here this star represents the point on the solvers where the entrapment is taking place. So, if the entrapment is taking place here, the fluid is actually a heterogeneous two liquid fluid. One like here it is a if we are doing it from an H2O CO2, and XCO2 is increasing, then we get one composite. You can calculate from the Lever rule here that on this particular so the fluid which is existing here actually is a mixture of two liquid. One liquid is mostly an H2O rich liquid with less of carbon dioxide, and one here which is a carbon dioxide rich liquid with less of water, which can be very well calculated by using the Lever rule on this kind of a phase diagram. So, corresponding, if this is 1, then this corresponds to the inclusion which is shown here. A aqueous component which is more in its volume, and a carbonic liquid which is subordinate, and it is also present as now this particular inclusion, it homogenizes into in an aqueous mode. This L aqueous, L carbonic becoming L aqueous means here after the partial homogenization of this carbonic phase, this with further heating the carbonic phase shrinks in its size, becomes smaller and smaller and smaller, with, as we discussed, the carbonic component will be executing pseudo Brownian movement very fast, and it will homogenize, and the clarity of the inclusion also allows us for a reproducible recording of the T total. Here it is homogenizing into liquid phase. Inclusion corresponding to 2 is here we see an aqueous liquid which is much lower in its proportion in volume. This is the carbonic liquid which is more in proportion, and here when we do the microthermometry we find that the aqueous liquid and carbonic liquid is homogenizing into L carbonic. Means exactly, if you remember what happens in a vapor rich aqueous inclusion where the homogenization takes place by expansion of the vapor and filling up of the whole cavity, exactly the same manner this carbonic component will expand and will fill up the whole cavity. That will be recorded as the temperature of total homogenization to the carbonic phase. Now, here the necessary condition that we apply here is that these two the total homogenization situations as we described here has to be temperature which should be exactly same ideally, or at least with a bit of a, depending on the clarity of the inclusion, or it is a essentially practical aspect that the determination of the homogenization into carbonic phase may not be that very distinct, of that very well recordable, reproducible in many of these situations. As you have said that data which will have to be some acceptable range of reproducibility can only be taking the ideal situation that here the temperature is also very well reproducible, and the temperature of total temperature of total homogenization, the T total in case of 1 is equal to the T total case of 2. So, that gives us a very clear cut or a very definitive idea that the entrapment was from a heterogeneous mixture of the fluids, but entrapment was essentially homogeneous, means the crystal when it is growing at one, because it also has to abide by the same conditions that we put for the aqueous biphase inclusions, means it has to be within the same these two inclusions have to be within the same grain of the host mineral. And they also have to be a part of the random 3-dimensional network. They are non-trail bound, and generally we say that okay, either they could be primary or their primary inclusions, or let us say that they should be co-eval, at least they must satisfy the condition of co-evality, that they must have been trapped at the same point of time, same conditions of pressure and temperature, same point of time. So, that is how when they are observable in a single grain of the host mineral, they will be same as part of the 3-dimensional network in the solid lattice of the host mineral, and then only we will we infer that the entrapment condition was what we are visualizing here, and the pressure value that we determine here, pressure and XCO2, because XCO2 is as visibly we know that they are going to be much different from each other. In this case it is much higher, XCO2 will be higher, here it is lower, and then the pressure and XCO2 value corresponding to the temperature at which the homogenization took place can be taken as the pressure of trapping, pressure and temperature of trapping. In this case we do not need any further correction to either of these two cases. Now, as is clear from this particular diagram, the entrapment could be anywhere on the solvers, and even one can I mean it is theoretically possible that if this happens to be the critical point. So, as I have said that entrapment or this situation could be anywhere on this solvers, even could be also on the critical point. Now, if we say that the entrapment was somewhere here, then the inclusions which are going to result, so for example, this is inclusion number 3 and this is inclusion number 4. So, in that case inclusion 3 and inclusion 4 may not have very visibly different or very visibly distinctly different in the proportion of their carbonic to liquid, carbonic to aqueous component. They may be very close by, very similar, but then we find that in one case it is, if they happen to be on the either side of, because of course they have to be on the either side of the critical point. So, in this is the aqueous rich part and this is the carbonic rich part. So, here the inclusion 3 and inclusion 4 may not have drastically different proportion of the two, the aqueous and the carbonic component. Still we can have the total temperature of total homogenization to different modes like one shown here, both to one to aqueous mode and the other to the carbonic mode, with still the temperature of homogenization of these two being same. Also the situation is that one can also have a condition pertaining to the critical point. So, it happens at the critical point, then we can have, so here it is not possible to have these, because it will be, if the entrapment on the critical point, then we will have a very fixed proportion of the carbon dioxide to aqueous component, and the homogenization will be critical homogenization is both. In a situation where we get many such aqueous carbonic inclusion with comparable proportion of the aqueous to the liquid, because it is essentially an asymmetric solvers. So, we get the proportion of the aqueous to the carbonic component, they may differ, and the homogenization is going to be on a critical mode. So, critical homogenization mode, as we know, that in the critical homogenization the vapor bubble does not shrink to the minimum observable size of just a black dot and then disappearing. Rather, the vapor bubble shrinks or decreases in its size to a certain extent, and after that the homogenization takes place by fading of the meniscus. the boundary just becomes indistinct and they become homogeneous. Such kind of critical homogenizations are very well observed in the aqueous biphase inclusions, but and ideally they also can be expected in such kind of mixed aqueous carbonic fluid. So, that kind of brings us within the limitation of this particular lecture series the discussion on the mixed aqueous carbonic inclusions and their applications of what we can know about the fluid characteristics. This is again this diagram which I also showed before, and you could see that in this case this particular inclusion which has the lower proportion of carbon dioxide is out of focus, and so that is why these two photographs which are from the same quads, but taken at different focus are presented here. And here you could see that the aqueous liquid is just a small part in the surrounding the carbonic liquid. It is a pretty regular shape inclusion where we can always take it to be a workable regular inclusion, regular shaped inclusion in which the data could be very well reproducible, and just within a with the closed spatial distance of it, but actually abiding by the rule that we apply, that we can take for at least more than 5 times the diameter of any inclusion that we are seeing. So, for the primary criteria, so they do satisfy, and here you could see the difference. So, in this case here the XCO2 is low, in this case the XCO2 is high. So, they do, and then when we homogenize we find that this homogenization is to the carbonic phase and this homogenization to the aqueous phase. In most of the cases even say we are talking about a situation like here where the liquid component is still lower, we can also have that. This out of focus inclusion also has a still low value of carbon dioxide, but such inclusions are much more prone to decrepitation or leakage when the temperature is high. These kind of inclusion which are just about 7-8 microns in its maximum dimension, these are the inclusions which are rather easier to work on, and the we can obtain the temperature of total homogenization in this kind of small sized inclusions, and also we can get back to their original configuration. So, a short review of what we discussed about the mixed aqueous carbonic inclusions. So, the pure carbonic inclusions are actually the easiest to identify, because as I said that since they would be very much close to their homogenization temperature, if we are seeing them in room temperature in the biphase mode, means they will be homogenizing within that temperature of suppose we are maintaining a room temperature of 25 degrees Celsius and the critical homogenization is 31. So, when we are seeing a biphase condition of a pure carbonic inclusion at 25 degrees centigrade, means it is quite close to its homogenization temperature there. So, the pseudo Brownian movement is pretty vigorous, and so that is how these are the inclusions which are very easy to identify, and also they are the ones the easiest to take the microthermometric measurements. And as I suggested, when we start a freezing operation, we first take the runs on these particular inclusions, because we only need to take two parameters TmCO2 and ThCO2, and these inclusions need not have to be relocated back for taking any other measurement. And even when we have other inclusions like aqueous biphase inclusions or the aqueous carbonic inclusions, and in the process of heating them, even if these inclusions get destroyed, even which is chances are even low, because they are very compressible liquid and their dP by dt slope is quite low. So, the chances of their decrepitation is also low. So, only thing is that if we want to go for any in situ non destructive analysis for these type of inclusions, for example, we want to take a Raman spectra, then this could be done prior to the microthermometry study, or the suggestion would be that to take the to subject them to such kind of non destructive in situ analytical technique before attempting microthermometry. And if you remember, when we plan our microthermometry, we break the wafer into workable size chips in which we can look for inclusions much more easily, relocate inclusions easily. So, as a standard practice, if we are disintegrating the fluid inclusion section to a number of such chips, it is not necessary that all of them have to be subjected to microthermometric experiments. Some of them could always be preserved for such kind of in situ non destructive analytical work. These are some of the practical tips. So, density and isochore are tricky for the methane bearing inclusions, because any concentration, any content of methane will decrease the density, but if you do not consider the concentration of methane, then we will end up with overestimating the density of the carbonic fluid. And the density and isochores are tricky for methane bearing inclusions, and they need to have a proper equation of state. I only have given you an example that how possibly it could be done, that by refining the parameters, the pressure correction in a modified Redlich-Kwong equation, the A and B parameter could be also fitted for a mixture of carbon dioxide and methane. With these parameters, the volume correction parameter is B, or say the non-ideal parameters A and B parameters have to be available for the methane. And sometimes these inclusions also do contain some H2S, nitrogen or argon, and those if available, such kind of systems would also such compositions, when they are detected, the density also appropriately should be calculated using the equations of state. The thermobatometry of these equations are reliable with the intersecting isochore method, and when we actually establish the coevality, which itself is also a tricky affair, and establishing coevality is mandatory. And only one note of caution when we are applying the intersecting isochore method is that say the diagram that we drew, the Cp of carbon dioxide, this is Cp of water or any brine containing known weight percent of NaCl, and we are constructing the isochores. So, this is the isochore for the aqueous inclusion, and this is the isochore for the carbonic inclusion. Now, we know that they will be intersecting at a temperature and pressure at a point giving us a unique value of pressure and temperature. So, the note of caution here is that if we have done the thermobarometry on coeval inclusion, this is a carbonic inclusion and this is an aqueous inclusion, and we infer essentially that at the time of entrapment the fluid was heterogeneous, a combination of liquid carbon dioxide and liquid aqueous. So, that means we are actually in the immiscible regime. So, if we are obtaining a pressure and temperature value by intersecting isochore method by using coeval, pure aqueous and pure carbonic inclusion, this PT value also should strictly correspond to immiscible regime. Any value of pressure and temperature that we are getting, and because we know that if we put it on a pressure temperature region in the diagram, so we know that this is pressure and temperature, if we are considering to be some kind of a bulk, if we reconstruct a bulk XCO2 and the weight percent NaCl in the carbon in the water, it will of course be not that very an easy an exercise. So, we actually our entrapment was we consider that the fluid was in the 2 phase region and this is the 1 phase region. So, if it so happens that the pressure and temperature value that we are determining here is falling somewhere here, then in that case it is an explanation has to be found out, or in that case it would be suspected that possibly there is something wrong. That means either they are not coeval, or there has been some amount of post entrapment compositional change, or that these two fluids that we are seeing as a carbonic component and an aqueous component possibly came from different sources, and what we saw them just as a coincidence that they were existing as immiscible fluids, but actually we were in immiscible, we are in a 1 phase regime. So, the only note of caution to be adopted here is any pressure temperature estimation that we do by intersecting isochore method, and those pressure temperature value has to be checked for the for their consistency with respect to the immiscible regime. And then aqueous carbonic inclusions are the most difficult ones on account of the uncertainty in the recording of the temperature of melting of clathrate, as we have discussed. It is a colorless solid, and its formation within the ice that is formed in the aqueous component is sometimes not very noticeable, but as a practical tip that I offered, that it is basically the diffused boundary or the meniscus between the two liquid, that is the aqueous liquid and the carbonate liquid, and the temperature at which the meniscus becomes very clear and the vapor bubble, carbonic vapor bubble starts moving inside the carbonic liquid component, liquid area, that gives us the surest indication of melting of the clathrate, and but that has to be reproducible. And the another important problem with these aqueous carbonic inclusions is that most such inclusions data cannot be recorded and cannot be used, because of the very simple fact that the most of them, the larger ones, eventually will decrepitate before total homogenization. That means, when we do the experiment, increase the temperature to a certain extent, then suddenly we find that the inclusion has decrepitated, leaked. The calculation of density and the construction of isochore in case of the aqueous carbonic inclusions is also quite I mean it is fraught with the inadequacy in the PVTX relationships, which still needs further refinement, and is still people are attempting to do that using many theoretical considerations. Like these days the molecular dynamic simulation has come to as one of the important and reliable tool in reproducing PVTX relationships in fluid mixtures. And sometimes also the fluid could also have calcium chloride, but what has been observed, the behavior of these inclusions do not change drastically much from a pure NaCl H2O CO2, or if it contains NaCl CaCl2 H2 and CO2. And so, this uncertainty in the density of the isochore is primarily due to the lack of experimental volumetric measurements covering larger ranges of these values. Means we do not have a full range of experimental data available. Had it been available, possibly it could have been much easier to calculate the density and the isochore. And so, refinement in modeling of the non-ideality of the system is still needs further refinement, and the theoretical considerations and more of experimental verification. So, with this we conclude our discussion on the fluid inclusion types, whatever basics we could discuss about the petrography, establishing the time relationship between entrapment of different types of inclusions in relation to the growth of the host mineral, primary growth, or the recrystallization at any later time, and identifying them, making a proper planning of the microthermometric experiments, and then have browsed through kind of the responses of the different types of inclusions like the aqueous biphase, aqueous polyphase, pure carbonic and the aqueous carbonic. These are the broadly the dominant types that if you look at literature where or any book or literature where you see descriptions of the inclusions, you will find these are the dominant ones which are described, and also sometimes the exotic ones like ones with containing graphite daughter crystal, or inclusions which are so very briny that they contain more than even up to 10 daughter crystals, or sometimes daughter crystal of a hematite, and sometimes even a flake of some micaceous mineral occurring as a daughter crystal, where whether it is actually a daughter crystal or a captive crystal needs to be ascertained. So, other than those ones, the most dominant commonly occurring ones are these four: the aqueous biphase, aqueous polyphase, the pure carbonic and the aqueous carbonic ones. And then we have also one of the important thing is that when we sit down to present the data, we also do use the same type of histograms for presentation of data on the. So, we have done a measurement on a lot of inclusions, pure carbonic inclusions. We would also like to present in the form of a histogram to see how is the distribution in terms of, because if we get a depression from the on the freezing point value from minus 56.6 to going to many to a much lower temperature, also present them as histograms of the density as well as the temperature of melting of ice and temperature of homogenization of the carbonic component. What we generally cannot do is there is no other way, but we will discuss that how when we go to specific case studies, that whether the fluid evolution diagrams that we present in case of the aqueous biphase inclusion or the aqueous inclusions only could also be looked at in combination with the results that we obtain from the carbonic inclusions, because they also do substantial, they represent a substantial part of the fluid characteristic in terms of the temperature and composition, and they are an integral part of the evolution of the fluid in any crustal domain. So, we will see them as much as we can through the case studies on or the application to the mineral to the fluid inclusions, to different types of situations, to ore forming environment, to metamorphic deformation and so on. So, hope to continue in the next class we will begin with the application of the fluid inclusion results. Thank you so much.